Hello and welcome back. We have learned in the previous two sessions on rock support design using rock mass classification systems. In this session, we will go through support design based on ground characteristics, particularly on ground pressure and ground deformation. Rock support using rock mass classifications are considered as traditional hard rock design. For weak, semi, highly fractured, and highly deformable rock masses, large converging deformation can occur after excavation, generally associated with high ground pressure. You can sense how much deformation occurred in this tunnel here. The background tunnel has suffered the squeezing, and the foreground is the re-excavated tunnel with the desired size. Tunnels in weak and poor rocks are supported by steel ribs or concrete lining to bear the pressure from the ground. By balancing the ground pressure, convergence is controlled. Different from rock reinforcement, rock support in underground excavation is designed to provide reactive pressure to balance or bear the anticipated ground pressure. For example, concrete lining in weak and poor rock mass provides reactive pressure against the ground and stops the ground from further deformation. Therefore, support is designed to cope with and to balance the ground pressure. There are two approaches to estimate ground pressures for support design. One is to analyze ground pressure deformation characteristics and how these interact with the support. Support design by this approach is based on ground support interaction analysis. The other approach is to estimate the ultimate ground pressure needed to be supported and design the support as load carrying structure. We can obtain the desired ground pressure using rock load factor, the ground's property, and ground pressure analysis. Both approaches are covered in this session. Let us start with the ground support interaction analysis and how supports are designed using this approach. First, we know that after excavation, the opening will start to converge. When the opening is supported, the support is under pressure from the surrounding ground, deforming into the opening. The ground pressure usually relaxes with further deformation. In other words, the ground is like a loaded spring. If it is an elastic spring, it eventually will stop and the pressure becomes zero. If the ground support has been installed in the opening, the ground converges against the support. Similarly, the support is like another spring, initially not loaded. When the support is compressed by the convergence, the spring is pushed and it starts to develop reactive load to push it back. That is, supporting reactive pressure is mobilized by the convergence in deformation. As the support pressure increases with further deformation, while ground pressure decreases with the further deformation. At one point, the ground pressure and the support pressure will be the same. When the two pressures are in equilibrium, further deformation of convergence stops. How do we use the ground pressure, ground deformation, and the support pressure to design support? Ground support interaction-based support design is primarily for weak and poor rock masses. The design will involve 3 steps. First, we need to establish the ground pressure deformation curve. That is, after excavation, how the stress is changing with the deformation at the opening. Second, we need to establish the mobilized support pressure curve. That is to know how the support element or structure develops the support pressure with deformation against the support. The design, as the last step, is to put the ground pressure curve and the support pressure curve together and to find suitable support that can deliver desired support pressure balancing the ground pressure. When the pressures are in equilibrium, converging stops and opening stability is achieved. Remember, the first thing we need to establish is the ground pressure deformation curve, i.e., stress and deformation around opening once the opening is excavated. Stress around an opening can be obtained by analytical solutions, numerical modeling, and field measurements. For example, the drawing and the equations on the right show the analytical solutions for the stress at a circular opening in elastic media. With stress, we can also compute ground deformation and the tunnel convergence around the opening. For elastic and continuous materials, the ground pressure deformation curve is also elastic. That is, a straight line. This is basically the elastic deformation, and that occurs immediately after excavation. Therefore, for solid rock material, which behaves elastic and continuous, the anticipated ground pressure decreases with deformation linearly. Deformation can end without support pressure if the stress is not exceeding the material strength. The linear relationship between the anticipated ground pressure acting on the support with change of deformation is shown here. In the y-axis, we use the term pressure required to limit displacement. It is the anticipated support pressure to stop deformation, which equals to the anticipated ground pressure acting on the support if the support were installed. For jointed and discontinuous rock mass, as we learned in rock mechanics, stress-strain relation for joint rock mass is no longer linear. Therefore, the ground pressure deformation curve is not linear. That is, as shown by the figures on the right, support pressure required to limit the deformation decreases with the deformation non-linearly. For good rock mass, deformation can still be ended if the stress is not exceeding the rock mass strength. For poor rock mass, deformation will continue if not supported, eventually lead to collapse because of the low rock mass strength. The ground pressure deformation curve is the most important part of the ground support interaction analysis. The support element in the structure are generally made of steel or concrete with non-stress deformation characteristics. The ground, on the other hand, as we have learned in rock mechanics, rock mass stress deformation characteristics are diurnal, discontinuous, inhomogeneous, anisotropic, and non-linearly elastic. Therefore, obtaining ground pressure deformation curve is the main challenge. As we seen earlier, we can use analytical solutions, but they are for simple models and uniform grounds. The most common method is using numerical methods, as they can handle complex models and the ground variations. The ground can be treated as continuous and discontinuous media using FEM or DEM. The figure on the right is just a simple example showing different ground pressure deformation curves obtained by numerical method for rock masses of different qualities. We can also get the ground pressure deformation curve from site monitoring by using field instrumentations and measurements. As we mentioned earlier, support pressure is mobilized by the ground deformation. By pulling the rock bolts installed inside the surrounding rocks, or by compressing the steel ribs and the concrete lining through convergence. Mobilized support pressure displacement curve is a property of the support material and the support structure. The load can be carried by the support, or the support pressure available shown on y-axis is proportional to displacement of the support. That is, the mobilized available support pressure increases with support deformation, with curves governed by the support material and support structure. The figure on the right here shows the support pressure displacement curve of steel bolts commonly used for rock support and the glass fiber bolt obtained from tests. As we can see clearly, the support pressure displacement curves of different support elements are governed by the material properties and can be obtained from tests. You perhaps should note that for steel elements, for example, bolts and ribs, generally have good yielding properties. The steel bolts shown here start to yield at less than 1 millimeter and can continue to deform up to 150 millimeter. If we put the ground pressure deformation and the support pressure deformation curves on the same diagram, we have the ground support interaction diagram, shown here on the right. Remember, the support shares the same deformation as the ground once it is installed. After the support installed, the ground will continue to deform and ground pressure will continue to relax, shown by the blue line. At the same time, support is being deformed and support pressure is mobilized as shown by the red line. When the support pressure curve meets the ground pressure curve, that is, the support pressure is equal to the ground pressure, then we have stress equilibrium. The ground will not be able to push into the opening further. That is, the converging deformation at the opening stops. The designed support has fulfilled its function, and the opening has stabilized. But we may have set the equilibrium at a different pressure level, and all have stopped the further deformation at the opening. This is illustrated by the drawing on the right. We may have a stiff support with very high support pressure and not much deformation has occurred. B is considered as medium support, while C uses yielding properties to provide yielding support, and D is soft support. Insufficient support, either support installed too late or support capacity too low, is shown by E. Optimum design is to support the ground at optimum stress condition, where deformation can rest. In this case, support B, C, and D are all acceptable. A is acceptable but not desirable, and the E is a failure design. This is the end of ground support introduction part. We will touch on this design when we learn about sequential excavation at the Netum in a late session. Now I want to move to the second ground pressure based support design approach. by estimating the ultimate ground pressure need to be supported and design the support as a load-carrying structure. As we mentioned, we can obtain the desired ground pressure using rock load factor. Rock load factor is perhaps the first rock mass quality classification system. It is indeed a rock mass behavior classification system meant for rock support design. In the rock load factor system, rock mass is classified into 9 classes, each with a rock load factor, HP. HP really defines how much load is expected to be carried by the tunnel support. In the times of Tazaki, in the middle of last century, was mainly steel arch. With HP, we can calculate ground pressure P to be carried by tunnel support. Given P equal to rock mass density gamma times HP. HP is given by the table on the next slide. Here is how rock masses are classified and what HPs are to be used. On the first column, we see the rock classes from 1 hard and intact rock to 9 sweating rocks. And associated rock mass and the tunnel behavior is given on the next column. The third column is a rock load effect HP, and the last column is remarks on support design. I will leave you to read through the table carefully and slowly. What I wanted to highlight is the last 4 classes, from class 6 to 9. They deal with very highly fractured, squeezing, and swelling rocks, which are commonly found under the Alps. Rock load factor provides the method to estimate ground pressure to rock support in weak, poor, and sometimes highly stressed rock masses. Supporting structures, for example, steel ribs and concrete linings, are designed as load-carrying structures. Concrete linings are the most commonly used tunnel support in weak and poor rock masses and soils. Concrete lining design adopts structural design practice by considering maximum or worst loading conditions in terms of compression, tension, shear, and bending for short-term and the long-term. The photos here show a typical tunnel supported by segmental concrete lining and the concrete segment. Segmental concrete lining today is a more or less universal tunnel support method for tunnels excavated by shield TBM in poor and weak rocks and in soils. Design of concrete segments follows concrete structure design practice. to meet the designed load. Design loads to be considered for tunnel lining are shown in the table on the left. Sections of worst or most critical loading conditions are identified within the length of tunnel, as shown in the figure on the right. Loads are analyzed and considered in the design of concrete thickness in terms of lining thickness and steel reinforcement. This is the end of sessions on rock support design and underground excavations in rocks. Here is a summary of support design methods for different rock masses and support types. Again, as we mentioned earlier, support for hard rock and generally competent rocks, empirical design using Q and IMR have proven to be very well suited. For weak and poor rocks, leveling and squeezing grounds, while rock mass classification systems can be used for support design, ground pressure analysis provide the good estimation on load and deformation to be carried by the support, and hence design accordingly. Rocks facing stress problems should always subject to stress analysis to design the appropriate support. With this table, I'm ending this session here. Starting from next session, we will learn about underground excavation techniques using machines and explosives. Goodbye and see you later.